Hello, my name is Izzuddin Al-Qassam. Here I'm presenting DAI5 or DAI5 Conscious Thinking Framework. I am master student of Mechanical Engineering in University of Indonesia. DAI5 stands for Dr. Ahmad Indra as initiator, and then the other I is intention, initial thinking, idealization, and instruction set. So let's begin to explain what this DAI5 is. First is Dr. Ahmad Indra as initiator. In this framework, Dr. Ahmad Indra serves as the initiator, grounding the process in a clear philosophical viewpoint. I'm my consciousness. These statements suggest a relationship between self-awareness and identity. It emphasizes that our thoughts and consciousness shape not only our understanding of reality, but also our action in it. The initiation point being a thought leader like Dr. Inda introduced ethical, philosophical dimension into the framework. His insights likely inspired users to adopt a reflective approach, emphasizing self-awareness as vital for conscious thinking. The second one is attention. This is the foundation where the solver consciously sets a clear, purposeful goal. The intention is deeply subjective, influenced by personal experiences and values, and aligned with the recognition of a higher purpose, particularly referencing the principle of Ketuhanan Yang Maha Esa from Indonesia's Pancasila. In this stage, the solver connects the technical problem to a broader, a moral objective. So it divides to two main stages. The first is purpose. In the CFD problem, my intention might include reducing emissions in an exhaust system, specifically in biomass gasification. This aligns with my broader values, or as the I5 emphasizes, reflecting on a deeper purpose beyond the technical solution. As Khalifah or leader on Earth, we have to maintain environmental sustainability, keeping our surroundings clean. The second one is subjectivity, reflecting on my personal motivation and connecting the problem with a higher purpose could involve integrating principles from my beliefs, such as contributing to society's well-being or a moral objective like protecting nature resources. The next one is initial thinking. The problem is thoroughly explored and understood in this stage, involving the collection of relevant information, basic principles, and hypotheses. The solver builds a holistic understanding of the problem's nature and context, often using tools like mass and momentum conservation equations. So there is three steps in initial thinking. So we begin with comprehensive understanding, gather all necessary data and information about the problem, such as flow characteristics, such as velocity, pressure, turbulence models. And also we define boundary conditions and the physical properties of the fluids, like density and viscosity. The next step is problem breakdown. decompose the CFD problem into smaller parts, such as identifying key physical phenomena, for example, laminar or turbulent flow, compressibility, and so on. And then the governing equations like Navier-Stokes and then energy equation. And also we must define the numerical approach, finite element, finite volume methods. And the last steps is hypothesis formation. We develop hypothesis or prediction based on initial exploration. For example, in case of biomass dryer, we might hypothesize that larger diameter and length will experience low efficiency of drying, which we aim to reduce. The the next one is idealization. Complex problems are simplified using assumptions and models, making them easier to solve without losing significant detail. For example, in fluid mechanics, assumptions about flow properties are made to reduce the complexity of equations and focus on key variables. Simplification, which means we apply appropriate assumptions to simplify the problem while maintaining the core physical essence. For example, for biomass dryer, we might assume steady-state conditions, compress compressible flow, or symmetry to reduce computational complexity. Model creation is we develop a mathematical or computational model based on the governing equation, for example, mass conservation, momentum conservation, and then apply the boundary conditions for our specific case. This might involve this might involve using turbulence models. Either we can use any turbulence models like key epsilons and then omega, key omega, and so on, or simplifying geometry to capture the essence of the flow while minimizing computational load. And the last one is instruction set. This final stage involves developing structured, step-by-step algorithms to solve the problems based on simplified model. This ensures a systematic approach guiding the problem-solving process to a solution. Step-by-step approach, which means we implement the problem-solving strategy by defining the sequence of tasks and solution algorithms. This involves discretization, the governing equation, selecting solvers, and defining grid resolution for accurate CFD simulation. The steps might include mesh generation, software setup, and post-processing analysis. And the last is execution. Run the simulation, monitor convergences, monitor convergence criteria, and adjust parameters if necessary. After obtaining the results, perform an analysis to validate the solution, ensuring the outcomes match our hypothesis or real-world data. By following this DAI5 framework, we can tackle any CFD problems more systematically and holistically. Thank you very much.